Hello and welcome back to HK Academy. In previous videos, we talked about compensator structure and loop design. But once we move from analog theory to digital implementation, something important happens. Even if your analog compensator is perfectly designed, the measured phase margin in digital hardware is always lower. In this video, I want to explain why that happens. We will look at two fundamental effects: the phase lag introduced by sampling itself and the additional delay caused by control calculation and PVM update timing. This is not a software bug and it's not a hardware limitation. It is an inherent property of digital control loops, and understanding it is essential if you want a predictable, stable behavior on real hardware. Let's start with the diagram on the left. When we sample a continuous time signal, we hold that sampled value and use it for the entire sampling interval. From a control theory perspective, this process behaves as if the signal is delayed by half of the sampling period. This is true even if the ADC conversion is infinitely fast, the MCU has zero latency, and the PVM updates instantly. This delay is not a hardware limitation. It is a purely theoretical property of the zero order hold used in digital control. As a result, sampling alone introduces an inherent phase lag given by the following expression. This means that every digital controller loses some phase margin, even with perfect hardware. Now let's look at the timing diagram on the right. In a real microcontroller, after sampling, the interrupt service routine executes the control calculations, and the PVM can update the duty cycle only at the next timing boundary, typically when PVM counter is equal to 0 or when the PVM counter is equal to the period value. The time between sampling and the moment when the new duty cycle actually takes effect introduces an additional delay. We express this delay as a fraction of the switching period, as shown here, where k represents the factor of the sampling period before the new duty cycle becomes active. In this example, we sample in the middle of the PVM period. As a result, the duty cycle update occurs roughly half a period later, so k is approximately zero point 0.5. If we sampled at the beginning of the PVM period instead, the effective calculation delay would be close to a full switching period, meaning k is approximately equal to 1, and the phase erosion would be significantly worse. So the closer the control calculation occurs to the PVM update instant, the smaller the phase loss. The total phase margin erosion is simply the sum of the sampling and calculation delays as shown here. Let's now look at some numerical examples. In this case, the switching frequency is 200 kHz and the ADC sampling frequency is also 200 kHz. This means the PVM period and sampling period are both 5 microseconds. Since we sample in the middle of the PVM period and update the duty cycle roughly half a period later, we assume k is equal to zero point 0.5. In the first example, we have a compensator designed for a 10 kHz crossover frequency with 70 degrees phase margin. The sampling delay introduces approximately 9 degrees of phase loss. The calculation delay introduces another 9 degrees. That gives a total phase erosion of about 18 degrees. So even though the analog design targeted 70 degrees, the measured digital phase margin will be around 52 degrees, which is exactly what we observe on real hardware. Second example is where a compensator is designed for a 7.5 kHz crossover frequency, again with 70 degrees phase margin. Here the sampling delay contributes about 6.75 degrees and calculation delay adds another 6.75 degrees. The total phase erosion is therefore 13.5 degrees, resulting in a digital phase margin of roughly 56.5 degrees. To summarize this slide, the half of the sampling period delay is inherent to the sampling process and cannot be eliminated. The calculation delay depends on your implementation, and sampling in the middle of the PVM period with k approximately zero point 0.5 significantly reduces the phase loss. Together, these two effects typically reduce the phase margin by 15 to 30 degrees, which matches practical measurements in digital power supplies. This is why we intentionally designed the analog compensator with a large phase margin so that once digital delays are introduced, the closed loop system remains stable and well behaved. If you want to go deeper into this topic, I cover it in detail in my courses. In the Type 3 compensator course, we focus entirely on understanding the structure, intuition, and frequency domain behavior of Type 3 compensators, what each pole and zero does, and how phase boost is actually created. This course builds the foundation needed to understand why phase margin erosion matters in digital control. Then in my digital voltage mode control for buck converters with TIC 2000 course, we take that theory all the way to the real hardware. We design the compensator, implement it digitally in C, integrate ADC sampling and PWM timing correctly, and verify the closed loop behavior on an actual C2000 based buck converter, including the phase margin you measured on the bench. If you are looking for hands-on material right now, I also provide a free buck converter toolkit on my website. It includes the Type 3 examples, LT-SPICE and Octave simulations, and ready-to-use reference projects that you can explore at your own pace. You will find all courses and free resources at hkacademy.com. Thanks for watching, and in the next videos we will continue building the bridge between control theory and real digital power hardware.